Good evening, Arjun. Hello, everyone. We'll just start in a moment. So, do you want me to discuss butterfly theorem again? Because yesterday was really a mess. And well, I did not even complete it. So, first you have a circle. Box. Yeah. So, you have its one chord over here. That is A, B, and there's its midpoint M, and then you have two chords passing through M. So let's click this. Okay, so Arjun, it might be an issue with your internet. This is C, this is B, this is E, and this is F. Okay, now E, we join EB, and we join CF. Let these intersect AB at P and Q to prove MP equals to MP. And you have that MP equals to MP. Okay, so we want to give it a try because there was some time yesterday as well, we might have tried it afterwards, or should we just discuss it? Sure. So we'll discuss it at 6:38, right? Or so let me draw what all ideas we had raised. Take the circle N. Okay, and you have this line, right? Let it intersect this one over here at suppose, I don't know, S. Okay, so we draw. No, I'm just repeating what we did. How far did we go yesterday? We complete the circle NED and let it intersect AB again at S. So you join SE and ST. Along with you might want to join SF and P. Okay, so let me take this bright color. You have this angle S. Oh, is visible properly. You have this angle SEQ. This one is equal to SDM, right? Because SEMD is slightly quadrilateral. And you know that EDM is equals to EDC and EDC is equals to EFC, right? And well, EFC is equals to EFQ. So you have that angle ESQ equals to angle EFQ, right? And what does that imply? Quadrilateral ESFQ is concyclic, right? So now you see power of 4. Okay, so you have that ME into MF equals to MA into MB. That is also MA squared, right? Because M is the midpoint of it. And now you can also say that PF. You also have that PD into PE. PD into PE is PM to PS. And well, PS is also PD into PE also equals to, well, PM into MF. How to track loading? PM into MF is equals to MS into MP. So try, yeah, so reload this. Okay, so over here, try taking MP is X, MQ as Y, MA as A, so this becomes A minus X, and QB as A minus Y. Okay, and PS has, yeah, actually, try using this. Try it over here and then we discuss for a few minutes. Oh, so you have that EQFS is concyclic, right? Because we showed that ESQ equals EFQ. So M is the intersection of the diagonals. universal. Yes, EFQ is QSC because ESQ is ESM is EDM, EDM is EDC, EDC is EFC. So see, you have that ME into MF is ME into MB over here. ME into MF in equals to ME into MB. Power of point of M in the original circle which we have, right? And MA is equals to MB equals to A. So that becomes A square and ME becomes ME into MB is also MS into MQ. And why is that so? Because ESFQ is one cyclic, right? So ME into MM equals to MS into MQ. Power of point of M in that circle. And MS into MQ is basically X. I am taking PS as Z. Okay. So MS becomes S Z plus X and MQ is Y. So that becomes X plus Z into Y equals to A square, right? And over here, PA into PB equals to PB into PE original circle and PD equals to PE equals to PM into PS, the way we have defined this point S. Okay, so that becomes A square minus X square equals to XZ. Try continuing from here. You basically have to prove that X equals to Y. Isn't it like done? Because from here you have that A square equals to X into X square plus XZ, and over here it's like XY plus YZ. Actually you write this X plus Z and over here it's Y to X plus Z, so X equals to Y, and we are done, right? So like here we have extensively used power of point, and that's how it's usually used sometimes actually, right? Now you take different power of point for different circles. We just use this, right? The power of, oh, as in butterfly theorem. Well, its power of points to introduce having such a point helps. Okay. Next thing, we all know that the power of point in a circle, you have center O, radius R, power of point P is OP square minus R square. If P is outside the circle, then it's positive. If P is inside the circle, then it's negative. And yeah, I'm speaking. Yeah. So OP square minus R inside the circle is negative, and if P is on the circle, then it's zero, right? Because OP will become equals to R. And then OP square minus R square is basically the length of the tangent. P, PT square, and you take PA into PB. This is also equals to PT square. Okay. And the converse is also true. If you have 3 points A, B, somewhere like this, P, A, P, and you're able to get a point such that PT, wait, a point on AB such that PT square equals to PA into PB implies PT is tangent to circle TAP. And well, it's extremely simple. You take this like this. PT upon PA equals to PB upon PT, right? And this angle is there. So doesn't it actually imply that this triangle are similar? PDA similar triangle PB, and when this happens, PTB equals to this, and that's exactly alternate segment theorem, right? For tangents. So let's move on to another problem. Okay. You have a circle. A, and you have two lines, two chords. Take this as B, take this as C. Okay, and you have a circle inside over here, tangent to AB and BC. It has center I. Okay, um, let this circle be suppose omega. AB and AC are tangent to omega, right? And I is the center of omega. So at point M, okay, you have to find the ratio Mi upon Mc. Yeah, in like numericals. Kind of like you have the radii. This is R and R for circle ABC, R for omega. Yep. It won't be like exact numericals, but it will be in terms of R and suffix distances. When you okay, there's some things like this circle is fixed, omega is fixed, okay, and A varies along the circle, and you have to basically put that mi upon mc is independent of the position of A. Okay, well, try this for like 5 6 minutes. We'll discuss it at 6:57. So basically, what all are you trying? I see. So let's, um, you have, yeah, that's true. Oh, okay, let me just name it properly. You are saying this is T, this is, okay, or let me reverse it better. This be T and over here be E, perpendicular, perpendicular, right? And let me join these MB, M's, okay? Now the question is asked just for MI upon MC, okay? And it is independent of A. So do you think there's actually any difference for it between C and B? I could have named it either way, right? So it actually gives us away that MC equals to MB. So how do we prove that MC equals to MB? This is 90, this is 90, alright? AD equals to AE because they are the tangents and AI is common. Let me remove this part from here. Yeah, it will be. I'm just proving that it's a midpoint. Okay, so these two triangles will be formed for it, right? So this angle is equal to this angle. Now let's take the circle center O. Alright, we join MO and let it intersect the circle. Let this point be N. Okay, so MN becomes a diameter. This angle is 90, right? I'm sorry, DM equals 2MC. No, not DM, it's D. Okay, sorry, that's fine. This is D. Okay, and this is here. Now we'll see this angle versus this angle. And this will be 90 obviously because MN is the diameter. Okay. Now this angle is theta. This is theta. DM is not MC, but let me say DAM equals to MAC. So DM is equals to MC. That's true. Okay. So angle BAM is theta. MAC is theta. MAC is MNC. How does he's not talking about D Arjun. This is also theta, right? MAC equals to MNC, and that means basically IAD equals to MNC, and both of them are right angle triangles, right? So these two triangles will be similar. Triangle AID similar to triangle NMC, right? Well, you have the triangle NM, it's equal. So AI upon NM equals to ID upon MC. Correct? Oh, you got MC, which is required in the ratio. So it seems something nice. What is this? Is actually MC into AI equals to what is NM? It's the diameter, right? And diameter is of length 2R. And ID is no capital Arjun R. So this will become MC into AI, so 2R R. Now you have that Mi upon M. So you have to find this, right? You multiply by Ai in the numerator and denominator, Mi into Ai, equals to MC into AI. Oh yeah, MI into AI. What is it? Is MI into AI fixed? This is MI. And hence AI. Yes, because that's basically the power of point of I with respect to the circle, right? And when I is fixed, so is the power of point, right? That's r square minus r square. So what does this become? R square minus r square upon 2r. And we're done. Because this is independent of A, right? And that's what we had to prove. Okay, understood? Yes, so the one more problem on PowerPoint. How does that really make a difference? That's a very specific case, right? And it won't differ anything because you're talking about a very specific case. And well, it need not be 2r equals to r, need not imply that mi equals to mc. It won't be. But this is not the in circle. Omega is not the in circle, it's just random circle. Okay, so let me draw your special case. It's like this. Okay, this is an oval. Yeah, it's not actually flat. We have this omega, take A, now wait, A, B, C. We have its in circle. That's pretty horrible, but let it be. We have its circle. This becomes our omega. This is A. This is this. We have its I. It is true, Arjun. We have this M. We have want to find Mi. That is, oh, Mi. In this case, Mi equals to MC, and so is R square minus R square equals to 2RR. This is the Euler's formula, right? Oh wow, we also proved Euler's formula. Euler's theorem or formula, I don't remember. Yeah, Euler has so many things on its name. So why is how we proved that Mi on MC is R square minus R square equal to RR. I know that how 3 by 4, this is not true. I know, right? Euler is bigger square. Arjun caps, that's the 9-point radius, not can't take even for an equilateral triangle. If r equals to 2r, then that becomes 4r square minus r square upon 4r square, and that is, well, wait. Well, for an equilateral triangle, MI equals to MC, so this is always true even for an equilateral triangle, and that is not true. Okay? Hmm. So, yeah. Well, do you want to move on to radical axis now, only, or should we do another problem? It's not true, Arjun. And should we do another problem? I did tell you, right? This is the Euler's formula. And if you take ABC as an equilateral triangle, then this is, we have this 90, right? R equals to over R, right? Um, well, let me see, just a moment. Yeah, that's what I was thinking. Mi upon MC. Yeah, Mi equals to MC is true, right? Over here, because this is C by 2, this is A by 2, this is B, and this is also A by 2 plus C by 2. So, incidental Mi is Mi equals to MC. And are we doing, this is 100% true. Oh, right. This is not exactly R square minus R square. This is the power of point of I with respect to omega. I did this in a random place, it will become R square minus R square, but it's not like that. It's the power of point of I with respect to circle ABC. That's what I was thinking for. Right? Now, in a random triangle, this will happen, but not in an equilateral triangle. It doesn't. I is fixed because omega is fixed. Alright, anyway, because that's given in the problem statement, like omega is given to us, so I is given to us in the circle. So a point has a fixed power, right? It is given, omega is given, and I is the center of omega. So I is given. Anyway, let's move on. So, do you want to do another problem on power of point, or should we move on to radical axis? Sure. Let me find a good one. Yeah, okay. So you have one equilateral triangle ABC. Okay. A. Um, why do you need the source to enjoy the problems? Okay, so yes, but we are not using big blue button. Um, because it has many technical issues like recording and stuff. That's why. You have the point K, L, M, N, P, Q. ABC is an equilateral triangle. So you have to, like, these are in order obviously given, to prove AK plus BM plus CP equals to BL plus CN plus AQ. Oh, it's any random circle which cuts all the three sides. Again, I have sorted these problems on my own, so I don't remember sources at all now. Okay, so um, try this problem. This the circle is supposed to cut PS is postscript version, and the circle is supposed to hit all the three sides of triangle ABC, just the way it is shown twice. Nothing urgent. This is the problem. You have triangle ABC. The circle is cutting, intersecting each of the sides twice without any extensions, and K element PQ is in the order as it's given. You have to prove that AK plus BM plus CP equals to BL plus CN plus AQ. Okay, so do this problem for like 5 minutes. We'll discuss it at 7:80. Any circle. Okay, order is a little messed up. This one, this one, this one. It's this. Oh, yeah, sure. I'll just check out that problem and after this problem first. Yeah. Anybody, meanwhile, try that problem. Anybody else has any other doubt on chapter 1? And after today, you can, okay, 50th as well. After today, you can try chapter 2 as well. Start the chapter. Kind of, they are arranged in difficulty, but sometimes they are not as well. It circles the radical axis power of point coaxial circles. Coaxial circles aren't used that much, so it doesn't matter. Okay. that 1985 problem is a pretty tricky one. Anyone discussed it? Yeah, sure, Arjun. Um, oh, did you see the hints for like it's given in Evanson's book with numbers? Like, did you try with those instead? Yeah, so if you just want a hint, so if you just want a hint, there are usually hints given, and for 50 problem there is. Yeah, so you can try with those hints and then discuss it about it. Okay. Till then, try this problem because I gave the wrong problem for a few minutes. So we'll discuss it at 7 to 8. Should we discuss it now? No. 4 minutes. So the problem is, yeah, you have this basically AK So you have AK, let me take a new color. I think, am I audible? Yeah, cool. So let me change the color. That is for and so change anyway. AK plus PM plus C3. Okay, and this is PL, CN, AK. Now do you see that AQ plus AQ into AP equals to AK into AL, like that, right? So we take this as A1, AK, B, CP as A3, this as B1, this as B2, and this as B3. And let the side be S. Okay, so this will be AQ will be B3 and AP is A minus A, S minus A3. AK is A1, AL is S minus B1, right? Similarly, A2, yeah, I wrote it right over here, S minus B2, and this is equals to B2, wait, no, let me write it properly. A2, S. AQ and for C, let's say B first, A2 into S minus B2 equals to B1 into S minus A1, and for C it will be B2 S minus A2 equals to A3 S minus B3, right? Now take these words. Okay, I'm not able to change my pen's color with it. This, sum them. Like, okay, sub plus minus plus will basically be A1 S minus B1 plus A2 S minus B2 plus A3 S minus B3 equals to B1 S minus A1 plus B2 S minus A2 plus B3 S minus A3, right? What is this basically? A1 plus A2 plus A3 into S minus A1 B1 A2 B2 and A3 C3 equals to B1 plus B2 plus B3 to S, and exact this thing, right? So these will cancel and then S will cancel and you have the result. Yeah, stop. Right? Now you see, it's such a problem. It's like for me when I saw this problem for the first time, it was like impossible for me to think that how where to start with if not power of point, right? Because like what else can you do in this? You have an equilateral triangle, a random circle, and some random sides. So this is how where power of point is very useful. Okay, so let's do another problem. Okay, the one Arjun said, problem 51, chapter 1. That's also IMO 1985 E1. Okay, so there's the circle. Actually, draw it. There's this circle. You have A, have B, you have side like this, A, C, D, ABC is concyclic. Alright, just let the mid center of the semicircle be O. And well, we have to prove that, and this semicircle is tangent to AD, BC, and CB. So to prove AD plus BC equals to AP. Alright. Um, Not really. It won't be, and how? It won't be a quadrilateral. It will be like a hexagon, and that's not very nice to work with, right? So like you have AD plus BC equals to AB. You see that AD, BC, and AB, like these three. Oh, right. Yeah, that is also not that useful because then B and C are just random over there, right? And we don't want that randomness for D and C. We want something specific. In such cases, you don't want to make the points like these more random. Okay? Like making the circle more random works. Let's given that ABCD is consecutive. Okay, so like you have AD, BC, and AC. So when you want to prove two sides equals to third, so what can you do? You can see that you take some point over here, I don't know, E. And if you prove that AD equals to AE, if we prove AD and BC, this is like the most useful way, most common way to do such cases. Yeah, phantom point exactly. Well, yeah. Want to show an existence of such point to prove that AD plus BC equals to AB, right? Okay, so the code went fine. Yeah. So okay. So like for the time being, let's assume that such a point E exists. Okay. So it's random point on which. And let's see that what if E is there's an existence of such E, then what will happen? Okay. The planes perpendiculars from O. Well, you have So what all things it will satisfy so that we can take such a point which is satisfied and then prove that AD equals to AD and BC equals to BD. We go the reverse way because otherwise it's pretty hard to imagine that what E point can be, right? So let's see. If you have BC equals to BE, then this is theta, this is theta, this is 180 minus 2 theta, right? BC will become 2 theta, and what will happen ODC? It will be theta, right? Because these two are tangents from the O is perpendicular component. Oh yeah, the tangents. It's actually nothing left now. Yeah, I know. That's a pretty bad drawing. This angle is theta, ODC is theta, and so is angle CED. What does this? Shouldn't BCEO become a cyclic quadrilateral? Right? BCEO will become a cyclic quadrilateral. And well, we got what thing was defining E, right? So instead now you take the point such that the circle DCO intersects AB again at E. Sure, Mayuk. So well, the I take a point E such that A, like I instead of proving the problem and assume that the problem is sorry, I assume that the problem is true and then go backwards. Alright? Like such a point E exists out so that AE equals to ED and BC equals to EC. Okay? This is not the proof, it will just help me to know that what point E will be. And that will just after knowing it direct. Okay? So you have that AE equals to ED and EC equals to EB. Okay? So if EC equals to EB, you assume that the angle CE ECB is theta. And if ECB is theta, then CEB is also theta because BC equals to BE. I'm explaining solution to start. Okay. So angle CBE will be 180 minus 2 theta. and so CDA will become 2 theta because ABCD is a cyclic quadrilateral. Now over here, this angle is 2 theta. This equals to this. Won't these each become theta theta? So obviously this equals to this. These two are the radii. No, it's 1.5 hour. Okay, so um, wait, this become theta theta because these two in this instead of the intersection of circle BCO with